So we're getting to the part of the semester where we can kind of pick what we want to cover near the end. And so mat types. Okay, so let me just ask you guys. I can show you in the book kind of the material that we have left to cover. And then we can decide if we like it. So we've made it up through a bunch of the chapters. We're going to go through chapters 10 and 11 today on mobile IP and unicast routing protocols. From here, we have several options because I think we have 4 classes left. There's multicasting. We can go through transport, UDP, and TCP. TCP would be good to make sure you guys really understand like rock solid. That's the important one. That's the one that's getting changed a lot as well. There's more in here on timers as well. And there's a third protocol that we haven't talked about before called SCTP, and it's one that's available to you if you want to write a program to do what Netflix does, for example. Not to make money, that's a different program, but different class. But this is the one that says, how's my stream going? Do I need to slow it up, speed it down? Do I need bigger packets, smaller packets? And so SCTP can help you with some of that. Then the application layer has some stuff that we don't necessarily need, except if you guys are interested, we can look deeper at DHCP and DNS. I wouldn't recommend we waste time on Telnet or FTP or on much of HTTP unless we look at HTTP 2.0, for example. And we can look a little bit at network management. They have some stuff on IPv6. There is a chapter on cryptography, which is interesting. And they have one on internet security in general. And you know, when you buy a plastic bottle, it doesn't do this. And the other class, they asked for stuff on media compression and encoding, network security, IoT networking, maybe 5G a little bit, and then more on NAT. I'm not quite sure what I'm going to do for that. So armed with that, give me some ideas on the stuff you guys are interested in that we can try to make sure we prioritize. What things would you like to know about that would be more fun for you? Okay. Yeah, okay. Security, what else? Oh, Bitcoins and things like that. We can talk about the impact it has on networking a little bit, and then try to see sort of where we think that's heading. There is some stuff that's happening on chips that will help. There's SHA-256 being built onto chips now, like on the CPU. So you can send encrypted data and decode it at the CPU. So people can't even steal your program by looking at the data across the data bus anymore. It's not even there. It's encrypted even there. It's just all the way into the CPU. It's insane. But that's where it's at now. So you can't even grab it. Even if you steal the laptop, you still don't know what the program does unless you have the key. So I can try to find some stuff. I don't know what I'll find on some of that and how much of it is, you know, ready to be shared in kind of a classroom environment versus just interesting articles that we can chat about. But there's fun stuff out there, and so give me a chance to kind of peek at some of that and put some things together. But for today, we have mobile IP to go through, and we may not need the whole class. I felt like I went too slow on mobile IP. This is one of those times where if I go faster, I'm not going to wonder if I skipped stuff. I'm going to know I did, because I think they about died. I think it was too much mobile IP. But there is some fun to knowing it. Even though you may never use mobile IP, you use lots of things all the time that mobile IP helped invent and helped chart the way for. Most specifically, virtual private networks, VPNs. So, you know, the programs you use to illegally watch American sports programs and the ones that I use to illegally watch Mexican sports programs from the U.S. Like, I can't get Rayados, so I have to, like, scrounge around and find a Mexican VPN provider and tunnel back to Mexico. It's a little bit humiliating, but that's the stage I'm at in my life. I'm just groveling for, please, does anybody have a stream that doesn't want my credit card number, please? So I always break down and call my son, and he's like, Dad, it's like, he sends me like 8 of them. Like, where do you get this stuff? You know, from friends. Like, I need different friends, I guess. But he sent me one for the Houston Astros last week, who are playing right now. In fact, it was like 4K, beautiful, perfect, full screen. I couldn't believe it. Like, this is illegal. This is better than what I pay for when I get it that way. So the issue is that YouTube TV just doesn't have the channels that I want. All right, so let's talk about mobile IP. So there's an old military analogy that we used to use that nobody knows anymore of your generation. So I'm struggling to try to find a new one, but I'll try to use a little bit of the Postal Service analogy, because that's what it is. It's based on sending mail to somebody in the military. So we'll talk a little bit about how mobile IP kind of works. So the problem they were trying to solve is an old one, and it's what happens when you move temporarily to work in a different location, or you're at a conference or something like that, and you don't want to update everybody in the world that you've like moved permanently, because you haven't. You just have been assigned someplace else for a while. So that's kind of the problem that we're trying to solve. It was very difficult to update your IP address. It usually required hard coding something into your system, and the network administrator had to come by and edit a configuration file until you got so sick of it you learned how to do it yourself and all of that. But now it's DHCP based, and we have VPNs. But the ideas behind them are tedious and important. So I'll get you through, and some of it will be hard. I will warn you guys will look at it and go, oh my God, am I supposed to like actually recognize, am I supposed to remember this? And I'll tell you when we get to that spot so you'll know. Okay, so if you're a moving target, it's hard to keep up with you, especially if you have a DNS entry. So you don't have to have a DNS entry, only if you want people to have a name for your computer. If you're okay with just having an IP address, then you don't need anything in DNS, only if you want to have a name for your computer. So this magnifies the problem, because if you do have a name in DNS and you change IP addresses, DNS has to be updated as well. And everybody who's cached your entry into DNS won't know the new entry until that entry expires and they get a new one. So that's another problem people felt like was painful and they wanted to avoid. So mobile IP also tackled that issue as well. So these are some of the issues that that happen. So here's the idea. I have my home network on the left. This is where I normally work. And I have normally an address in the 131.5 network. And I'm going to copy this over because it would help to start even from this first slide showing some changes. All right. So what I don't see on this diagram, which of course we have, is what my public address is on the internet side of my router. So this is the address of the home network, and you guys remember about the way we're supposed to draw these diagrams. This gray is supposed to include, this part of the router as well, right? Remember? So it's include the router port. He always leaves it out. It's trying to make me crazy. So, but it's not supposed to look quite that bad. That's like a tornado hit or something. Okay. And what I don't see on this diagram that I would like to know, that I'm very curious about, is what is my public IP address. So right here, my public IP address might be 20.2. And I'm going to make these IP addresses short so we don't go nuts, because I'm going to write like 100 of them today, okay? So this guy's IP address is 131.8, okay? All right, I'm teasing a little bit. And this network is 131.0/16. Over here, this router's public IP address might be 15.2. I'll give it, I'm going to make it a 3. Let's see, have I used 3? No, I haven't used 3 yet. So this guy's address is going to be 14.9, and his home address is 131.8. All right, so what's going on here? This is me. I have moved. I used to be in the yellow box on the left, but I'm now located in someone else's network. And as you can see, this other network has a different subnet number. It's 14.0/8. So normally what would happen is I would have to get an address from that network. And I did. I got one right here. So this is the network. I DHCP'd and I got a new IP address. But nobody knows I've moved. So what I want mobile IP to solve for me is this problem of not having to teach anybody anything new about where I am. I don't want them to have to do anything. I want them to still send packets like they always have before from someplace on the internet to home, but I need someone to recognize that I've gone and to take the packet and send it right back out over the internet again to my new location. And then when I send something back, I'll go in exactly the opposite direction, and the same thing will happen. So whoever this user is here, they will never know that I'm someplace else. They will continue to send packets to 131.8, and they will get packets back, but they may not quite be this number. They may come from the router's public address. We're not going to worry about too much of that. Okay, so that's the idea. So I'm going to plow ahead, and then we'll come back to this diagram a little bit later. So the first thing we do is we create two new software packages. We're computer scientists. That's what we like to do, is create new software. So we're going to create something called a mobile IP home agent and a mobile IP foreign agent. And let me just stop real quick and do one quick little thing. Sorry. And do that. Okay, sorry. Okay, we're back. So this home agent is the thing that's going to take this software and intercept it and turn it back around. He will also accept software that's coming back from me and make it look like it's coming from where I always was. So again, the illusion is for this user not to have to do anything different at all. Okay, the foreign agent is also playing a part in this because the foreign agent is going to help me let my home network know this is where I am. Hey, it's like another mother in the neighborhood when you were little texting your mom saying, hey, you know, he's over here, he's fine, can he stay for dinner? They're having fun, he's done his homework, you know, is that okay? Yeah, right? So it's exactly like that. So it's up to kind of the moms to kind of sort that stuff out. You're not old enough to be responsible to do that on your own. So that's what this software is. It's going to be running on these two routers. So yet another thing we want the routers to do. Okay, so home agent and foreign agent. Sometimes you have the software that's running in your mobile host and the software that's running in the router, both running together inside the host. And this router doesn't have to do anything at all. This host turns on, he makes the connection back to the home agent, and he handles everything himself. Yeah, we call that a VPN. Okay, that's what a VPN does. You show up at Starbucks. Starbucks doesn't need to do anything special on its router for you. You can just start up your VPN software and connect to wherever it is. You're perfectly capable of doing all that with your VPN software yourself. Okay, so in the mobile IP world, they came up with that idea first, and they call it a co-located care of address. I prefer VPN. It's a lot shorter for one thing. So the three phases in getting this set up are somewhat similar to what we do to VPN. They're exactly what we do when we have a co-located care of address. So the first thing we do is figure out, is there somebody at my home network that if I were to travel would be able to send me my packets? So I send out a broadcast message and I ask, just like I would any other protocol, broadcast a message out and see who responds. Hopefully the router will write back and go, I know how to do mobile IP, I can help you. Let me know when you get to where you're going and I'll forward your packets to you. Great. So the second thing is registration, because when you get to this new remote location, you have to reach back and let your home agent know, here's where I've landed, here's where I am. Please start sending me my packets. And in the third phase, all this complicated transfer happens. Now, yes? Yes, I will show you. I will show you in a diagram. So the picture makes it a little easier. So we'll walk through it in text, but then I'll dig in a little more. So the first step is agent discovery. So I need to figure out, if I were to leave and go to another location, is there anybody on my home network that can forward my packets to me? Is there anybody here that knows how to speak mobile IP? So you will discover that by broadcasting out an agent discovery message and to see if your router responds to it. So if you have mobile IP set up, your router will respond. Yes, I do mobile IP. Go ahead and travel. Whenever you land, wherever you get to where you're going, open your software, tap me on the shoulder, let me know where you are, and I will start forwarding you your packets. No problem. And then let me know when you get back by broadcasting out another message from inside the LAN, and I'll go, oh, you're back. Okay, good. I can stop doing that. So that's basically how that's going to work. So I have a big, long-running disagreement / serious doubt over part of the way this book describes this protocol. And I cannot figure out how it could be right. But what's bothering me is the author's really good. He just doesn't make mistakes. And I cannot fathom that he would make a mistake this big. But I've tried and tried for years, actually, to reconcile what he has on this diagram with what I believe to be reality, and I just cannot figure it out. So you probably won't use mobile IP ever, but if you do, make sure you do a little more work on your own, okay? Because I'm not confident that this is correct. And I've explained it enough times. I think if it was correct, I would have figured it out by now. All right, so let me explain to you what I'm talking about. So before I leave anywhere, this is me on the left, I send out a broadcast message. My home router responds saying, I know how to run the home agent package of mobile IP. So this home agent is the name of that software package. Okay, so I'm good. I write that down, I record it in a configuration file, it be stored by my software, and then I leave. And I magically pop up over here on the other side of the network, someplace else. This is also me. Okay, that's not very clear. So when I was on the left, if I kind of scratch this out for you guys, when I was on the left, I was on this LAN. All right? And now I'm on a different LAN over here. I'm separated by the internet between us. Okay? So this LAN is your LAN, but this LAN is also my LAN. Get it? This LAN is your LAN, this LAN is mine. Anybody know that Arlo Guthrie song? Okay, never mind. It's a mobile IP joke. I told you nerd jokes are terrible, right? We don't have very many, so when I get the chance, I trot like one of the 3 or 4 out there. There's not too many. And you guys know the UDP joke, right? Well, I could tell you the joke, but half of you wouldn't get it. That's the joke. Because UDP doesn't retransmit if the packet's lost, so I could tell you the joke, but half of you wouldn't get it. So. But thank you for that. That made it perfect. So at least we had a few people actually laugh at a stupid joke, which most of the time people just look at me like, when is this over? Okay, so I've moved to this other network, and I send a new packet out. It's a different solicitation, but I'm looking for somebody to step up and say I'm a foreign agent. These things very often are one and the same, inside the same host. So you don't need the router. If they're both together, what we call this today is a VPN. Right? You still need to know this, though, because even if you're going to run a VPN, you have to know the address of the VPN concentrator. That's where you're going to open the VPN connection to. So you still need to know stuff about home. And you still have to be given a configuration file that you take with you, your VPN profile. Okay, so I get to where I'm going. I solicit for it. Now there's registration. I basically say, Mr. Router, here, would you let my router know where I am, and would you ask him please to forward things for me? And they say yes. So all this is okay. I don't have any problem with any of this. Where I have a problem is the very last box that says data transfer. So this is the person that was trying to reach me. This is like one of you. This is not somebody running mobile IP. This is the person who's not supposed to know anything different. Right? This is the person who's supposed to still send me stuff exactly the way they always have. Well, if I'm going to start sending data from here to you, it's got to come from this 14.9 address because that's the subnet. It's not over here. If I try to send something with this address over the network, it's going to get dropped and error messages are going to fly. It won't work. This is not the LAN. The LAN that I have, this is the address. And if I start sending you something here, how is it you don't notice? How can you not know that I'm not really back at home again? This doesn't work, and it's also not the way a VPN operates. So I don't think the transfer starts happening between these two. I think the transfer happens in a very different way. So I'm going to show you, we're going to skip some of this stuff. If you want to see what the packets look like, they did do one very clever thing that's worth mentioning. Instead of inventing an entirely new protocol to do this, as far as packets and all that, they borrowed one of the ICMP error messages called an advertisement message. And they used that advertisement message because it had some sequence, it had some type numbers left over. So they took one of them and used it for mobile IP. So when they broadcast out a agent solicitation message, they're actually just sending an ICMP router discovery message. And routers are okay answering those. Everybody's okay answering those. It's a friendly message. Who's got a problem with that? So unlike trace routes, which everybody wants to drop. So they were clever. They did do something smart with that. So here's a more detailed diagram of what's going on. So I have now moved to the bottom. I'm down here at the bottom. And so I've got a user on the internet who is sending me a packet, just like they always have, to the same IP address as before. And my home agent is going to intercept that packet and send it over a tunnel to my new location. And I will receive the data, and I can talk back and forth, but I have to do it all the way back through the home agent, all the time. There is no data transfer directly from this person's IP address on this network to this person's IP address on this network. I don't think that can happen. I think it has to go back. I can give you some reasons why. When he wants to open a connection to me, let's say I'm running a little web server, okay? And he's got a little, he's got a web browser, and he wants to open a page and type in my URL to get my web page. What's the very first packet he's going to send to me? What kind of request? So you're on the right track. So the application layer is going to, when you hit return on your browser, what's the application layer going to generate? It's a browser, right? So what protocol does it speak? HTTP. So it's going to generate a GET message, right? Get index.html, HTTP 1.1, host colon, and then the name of the host. So that's the application's message. Where does that message go? That's where's inside my computer. Where does it go in the stack? It's at the layer 5. What's the layer below? Transport layer. And is it going to go to UDP or TCP? Which one does HTTP use? TCP. So is TCP going to immediately send that GET message across the network? Yeah, it has to go down to the next layer, but it stops. It doesn't do anything with the GET message. It doesn't even think about sending it yet. Before it can do that, what does it have to do? If you walk into my office, before you start talking to me about your problem, what do you do first? You say hi. So what's the TCP version of saying hi? The handshake. Really important. It's got to do a handshake. So I can show you the handshake happen if you want. We can try going to a web page and you can see the handshake happen. So let me open up a browser and we're going to type in TCP. I don't want to do that yet. TCP. Come on, don't be a jerk. This is like super slow to search through these on this computer. It's so bad when I go home to my server and I try doing stuff there, it's just 1,000 times faster, and it just, like, please somebody give me a new laptop from Apple. Okay. So let's look at TCP. Here's my send messages, and I will say OK. All right. Oh, in fact, it looks like I already have a couple, but that's okay. I won't get tricked. So what I'm going to do is go to the New York Times. All right, that's enough. Stop. And we'll close that off. All right, so what I see here are a whole bunch of send messages. So if I get rid of this filter, what I'm hoping I'm going to see after those are some send, SYNAC, and ACK. That's the three-way handshake. And these are the first packets to this IP address, 199. That's the New York Times. You don't see any other 199 addresses before this. So the first packet TCP sent out was send, SYNAC, and ACK. And then the next thing that sent out after that, because it's a secure website, was client hello, which is the TLS negotiation message. And inside of that comes my get message, but I can't see it because it's encrypted. Yeah. But at least I know where they're going to. I can see the website they're going to. All right, so if you think you're hiding where you're going by using HTTPS, you're not. I can still see the IP address. I can still look it up. And you can still see where they're going. So be very careful, gentlemen. Okay. All right. So that's what's going on. That's the first thing that we do. So if I do a handshake to this IP address, and the response comes back from over here, how's that supposed to work? It can't. So the handshake and the response have to be from the same place. All right, so here's where we need to get into a little bit of nitty-gritty detail that's probably going to drive some of you guys insane. Yeah, so number 4 is incorrect, is what I'm claiming. All right, so let's draw something to show. How many of you, if I ask you to describe the difference between encapsulation and tunneling, feel like you could absolutely do it? All right, no one? Okay, so let's draw some diagrams. So let's say I'm a user and I build a line. I build a rectangle. And I'm going to draw this rectangle for reasons that you'll see in a minute a bunch of different times. Okay, and this rectangle is a message from my application. So it could be the get message, right? It could be my get HTTP message. That's going to be in an application container. I send it down from one layer to the next, from layer 5 to layer 4, which you guys said was the transport layer, right? Isn't that what you said, TCP? So what does TCP do with this? TCP puts a wrapper around it with the header at the beginning, right? And that's going to get passed down a little further. And I don't know if I need all these, but it's easier to do it while I'm here. So TCP is going to put a header in here. And that's called encapsulation. Taking the contents that you've been given from a layer above and adding your own stuff around it, putting all of that inside of a capsule just like medicine. On the way up, you're going to decapsulate it, take things out of the capsule, throw the capsule away, and you still have the contents. All right, after layer 4, where is this message going to go? To IP, correct? So I still have my app message in here. And this normally would go to layer 3. And what layer 3 is normally going to do is put a wrapper around it. And here we're going to look at a little more detail. So my source, in this case, if I look at my original diagram that I had here, my source was, let me think how I want to do this exactly. Okay, the person that was sending me my packet was using a different address, and I don't have them on this picture, so I have to draw them. Let's go up and draw them. So here's this remote user. This is the person who's not supposed to know anything special. And let's say he's using the address of 50.6, okay? 50.6, and my address was 131.8. 50.6 and 131.8. So the source address here is going to be 50.6, and the destination is 131.8. Does that sound right? I think that's correct, isn't it? Okay, so that's the source and destination for IP. And what needs to happen is I need this router to intercept that traffic. He will get it. It will be sent by the internet to him because that is where 131.8 lives. So no change there. But he needs to send it to me now. And what this diagram shows is that I've got to build some sort of a tunnel to get that done. And here's how that tunnel has got to work. I'm going to have to build a big tunnel that's going to carry the traffic from here probably all the way to me. Maybe you can figure out a way to stop the tunnel terminated at the router, but most of the time I think you're going to end up wanting to build the tunnel all the way to the mobile host. Why? Well, go back to the other diagram. Because if the router takes this packet and turns it around on the network and puts it back out on the network, where is it going to go? You haven't changed the destination address. It's not going to go anywhere. It's going to be like, why are you sending this to me? This is your packet. So it's never going to get sent to my new temporary address. And my temporary address is this 14.9 address. So what I really want to have happen is when I drop this packet on the network, it goes to 14.9. That's where I really need it to go. I'm okay with the source still being 50.6. Maybe that's okay. But I need the destination to be 14.9. How am I going to do that when I've already used up the source and destination? This is a lot worse than ARP. I cannot find the destination on my local LAN. That trick's not going to work here. So the only thing I can do is something different than encapsulation. I'm going to do what we call tunneling instead. So I'm going to take this entire packet with the wrong, it's right in some ways, but it's wrong in another, IP address. And what I need to do is I need to send this whole thing to the laptop at this new location. And so the way I'm going to do it is put one IP packet inside of another. And so for this one, it's still the same source and destination IP that it was before. in orange. Nothing's changed. But now I've buried that inside my payload. I mean, IP doesn't care what you tell it to carry. It'll carry music, voice, IP, it'll carry TCP, some new protocol that you invent tonight. It couldn't care less. It's just an envelope. You can put whatever you want inside the envelope. All right, so I'm going to have a second source and destination address because I have a second header because it's a completely different IP block in front of it. And this source is going to be what? Well, I'm going to jump ahead and pretend like we're in the land of VPNs. So this destination address is 20.2 on my router. So I'm going to set the source of this one to be 20.2 and the destination to be 14.9 because those are the two ends of the tunnel. Anything I pour in one end of the tunnel at 20.2 is going to come across the tunnel and pop out the other end at 14.9. And so what does it actually mean for it to be a tunnel? All it means for it to be a tunnel is that the packet is hidden inside the payload. There's nothing you've changed about any of the routers along the way. So if I stop in the middle of this diagram and I ask a router that's sitting, let's say right here, hey router, you just got a packet. I'm told it's part of a tunnel. What do you see? The router's going to say, I see a packet coming from 20.2, and it looks like it's going to 14.9. So I'm going to send it to the right because that's where my routing table says this 14.0/8 network is. And you don't notice anything funny about it? No, not a thing at all. It's just a regular IP datagram. I wonder why the guy's calling it a tunnel. Well, if you look deeper inside the packet, you'll see another IP datagram, and they'll go, oh, that's kind of strange. But the router couldn't care less. He looked at the source and destination, he did his job, he sent it on. So it's only a tunnel because we've come up with this idea that it's somehow different. And what's different about it is I've kept any of the routers along the way from seeing the truth. And the truth is I'm sending a packet from 14.9 to 131.8. And if any of these routers along the way see that, they will turn the packet around and send it right back to 131.8 because 131.8 is over on the left side of the diagram. That's where that network lives. And if they see the packet, security is so bad now that if they see this packet coming from a direction that they don't normally see 14.9 traffic, they will drop it and set a security alert that no one will pay any attention to. Okay, so to go back to our diagram, the way to describe it technically is with this. Did I really draw on my diagram, my beautiful, perfect diagram? God. Now I have to do the whole thing over again. No, I'm kidding, don't worry. Okay, that's not too bad. I can live with that. So that's what makes it to the other end. And that ends up going down, I don't know, what do we need next? We need Ethernet in here, right? So I'll just draw the colors, the rectangles. I have really taken off with colors this year. Like much more beautiful images, I hope you guys think. So here's Ethernet. The only thing different about Ethernet is it also has a tail at the end. Remember, it does checksumming. So you have a CRC error correction code down here at the end, and you have Ethernet here. Okay? So when it gets to the other end of the tunnel, which is inside the laptop, this will get removed. Then this will get removed. And what you will hand your PC's VPN software is this packet. All right, let me give you another example that's much closer to what you guys do, and I'm going to use Cisco as an example. So here's Cisco San Jose, and I'm going to use a different color. So they have a VPN concentrator, and it's part of their router. So it's got a public IP address of 160.22. All right, so behind that sits the Cisco LAN. And they have printers and other users, and they have a firewall. Oh, what did I do? And that all sits back in here. And their connection to the internet is right here. Okay, I have sportstream.net. Sportsnet.stream, I think, is the one my son sent me to. I didn't even know there was a .stream. I'd forgotten. And here is its server. And it lives at, it's illegal, so it lives at 66.66. How about? Make it like the devil or something. Okay, so here's where he is. And I am in Monterey at the Sheraton Ambassador Hotel on my laptop. And I have a 10 dot private address. And so I'm going to get natted on the way out the door. And I'm going to get natted to something that's a 8.23. That's going to be my public address. So we'll add nat to make it a little interesting. So if I want to make this work, this is the USA, and this is Mexico. So I guess this is the wall, huh? Okay. Did you guys hear what's going on in Tijuana? Well, probably. So the Mexicans are stealing the concertina wire off of the wall in Tijuana to use it for protection for their own houses because crime's kind of bad. And there's a late night talk show host whose name I don't know, Trevor something I think it is, and he almost fainted on beer. He was laughing so hard. He said thinks it's the funniest video of his life because he goes on with it for a while. They show a little video clip, and he's like, well, if they're going to steal the concertina wire, why not just steal the whole wall? And he said, can you imagine now? Like, people built this $8 billion wall, and nobody ever stopped to think maybe the Mexicans will steal it. And he's like, are we going to build another wall for the first wall? Because I can see it now in Tijuana. The news is going to be there, and there'll be a Mexican homeowner who's going to say, here's my new security system wall, and you know what? I got the Americans to pay for it. I thought that was one of the funniest things. That would be awesome. So he's been saying all this time, I'm going to build a wall, and we're going to make Mexico pay for it. And we are building walls for the residents of Tijuana, and the United States is paying for it. How funny is that? Is that not like classic? So just goes to show what you get when you're rude to people. Okay, so if I want this to work, here's what will happen. If I send a packet directly from my address to this address, it's not going to work because they see that I'm not in the U.S. and they won't stream the sports to me. All right, so what would that packet look like? So the source would be 10.11, and the destination would be 66.66, correct? Okay, that's at point A. What's it going to look like at point B? This is without a VPN. All I did was send a packet to 66.66. I'm running NAT. This is a private address, so what's the source going to be? Exactly. And the destination? What? No, there's no VPN yet. All I did was send a packet to this destination address. The same. There's never anything wrong with the destination address in any of these schemes. Right? Okay, so this is without VPN. What's going to happen when I turn on VPN or mobile IP? The first thing that's going to happen is a tunnel is going to get built between this VPN concentrator and my laptop. So my laptop, in order for this VPN to work, the vision is that it's just like you're back at work. It's like you're there. Okay, let's pretend I'm there. I'm there. What's the first thing, the first packet my laptop's going to send if I really was there? I come in the morning, I sit down at my desk, I open my laptop, somebody's running Wireshark. What's the first packet they're going to see me send? Yeah, what's that called? Do you remember? Exactly. DHCP. Do you guys remember that protocol? This is the one that you run when you don't have an address. I can show it to you. So I'm going to start up Wireshark. Oh my gosh, I was running Wireshark that whole time. Oops. Okay. So what I'm going to do is open up Wireshark, but I'm going to have it watch my Wi-Fi connection. My Wi-Fi connection is not working right now. Now when I do this, it's going to put a glitch in the recording for a minute, but I'll bring it back. So I'm going to turn my Wi-Fi network on, and what happened every time in my life up until yesterday when I tried to demonstrate this, as soon as Wi-Fi turns on, it takes over, and there it did it. All my packets are now going over Wi-Fi. It's getting some identification stuff out of the way. In a moment, WebEx is going to figure out that it has, oh, it stopped. It still quite hasn't negotiated a connection. Who's it trying to join? Still getting all kinds of queries. It's trying to join eTESM. Let's switch over to Tech instead, because that one's not working. So I'll switch over to Tech. I see another DHCP here, and it's going to try to join, but it's not working. Why am I not surprised? I have nothing but trouble with Tech's Wi-Fi networks. But at least we got the stuff out. Okay, meanwhile, the people over on the Ethernet network think I've probably forgotten about them. So I'll go back over to that. So what I want to do here is look for DHCP, which I can't find it. Do you guys remember why? Anybody remember the old name for DHCP? Boot protocol. Why we don't just change it in Wireshark, I don't know. But here it is. So I found it. It's the second packet that was sent. Well, then what was the first packet that was sent? The first packet was an association beacon message from the Wi-Fi router saying, would you like to join me? Who are you? I noticed you're trying to connect. All right, so the first one that I sent was a DHCP discover message. Okay, and who's going to, when I continue on with this boot P, what happens after that? Well, I don't get much help because this thing didn't work very well, but down at the bottom, I finally got an address. After a bunch of these request messages, I get an offer back saying, maybe you have lots of other offers, I don't know. Maybe you're already going to the prom with someone else, but if you're not going with someone, would you go with me? Right, so you get an offer from however many are out there, and if you like this offer, then you acknowledge it with a request saying, yes, would you please go? I would like to do that, and then go, great, all right, I'll see you on Saturday, whatever the message is. I told you this stuff is exactly like stuff in your life. All right, so I finally got an offer. So my question is, where did the offer come from? This offer says, I would like for you to have this IP address. I'm going to give you 10.15.219.114. Who did it come from? I just did this at Tech. I'm not running any VPN software or anything like that. All I did was turn on my Wi-Fi and ran DHCP. Someone offered me this IP address. Who does this address belong to? Apple? The University of Houston? Tech. It came from Tech. Okay, so let's go back to our diagram. I turn on my VPN software. And remember, the VPN software makes it look like I'm really back in San Jose. That's the illusion that it's supposed to create. So the first thing it's going to do is send a DHCP message over the internet, tunneled into San Jose. It will pop out the back end of this VPN concentrator, and it will be a DHCP broadcast message that's sent to everybody on this LAN, including the router. The router will respond, and the router in San Jose will give me a Cisco IP address. It will come across the tunnel because these two guys are making it happen, and so I will be given a new IP address. And it just so happens that the new IP address is also going to be a 10 address because both Tech and Cisco use 10 dot network numbers. Most organizations use 10 dot network numbers. They're private. We reuse them over and over and over. That's why they can never be public addresses. That's why it had to be NATed before it could leave the hotel. Okay, so now my VPN software is turned on. This is my IP address. It comes from this network over here. So the VPN software is like magically working. But all it's doing, remember, all it's doing is this. The VPN software is doing this. It's taking every packet that I've got. This one is the Cisco address, and this one is the hotel address. So what the VPN software did is it wedged itself in right here. It inserted itself between layer 4 and layer 3. And no matter what I send it, it's going to require that it always go one place, back to Cisco. Every packet I send out of my computer, it's going to encapsulate it. It's going to completely ignore the IP address I'm trying to reach. And it's going to ignore what my Cisco assigned IP address is. It'll put it in orange, and it's going to take that whole thing and stick it in a packet that the Sheraton will deal with. So that packet has to have my Sheraton IP address. It will be NATed on the way out the door to the Sheraton public address. It will go across the open internet back to Cisco to the VPN concentrator, because that's the only place this VPN software will let me send packets. Every single packet goes to that VPN concentrator. When the concentrator gets it, it throws that header out, and what it's left with now makes sense. It's left with a packet that says it's coming from a Cisco IP address. Okay, well that makes sense. I'm at Cisco, right? It's moved the packet to Cisco, and it's going, where are you going? You're going to this sports streaming site? Okay, that's fine. I'll do that for you. I'll send it out over the internet for you. So when it gets to the site, they think I'm coming from San Jose. Right? So it wedges itself in. You'll hear this called shim software, wedge software, layer 3.5, but it's basically inserting itself. It's another IP stack that inserts itself between layer 4 and real layer 3. And so to the real layer 3, it looks like it's just a really weirdo TCP or something, because all it does all day long is send packets to the same place, never any place else. And the only person that ever sends it packets is the same place. It'll drop all the rest of them. It'll only accept packets back from that VPN concentrator at Cisco. Everything else it throws out, with a couple of exceptions. One of them is the time of day. It will set its clock still locally on where you're at. So if I go back and look at this one more time, now with my VPN, my source address at point A, I guess I could use the same colors, it wouldn't kill me. At point A, what is my source address? If I look with Wireshark at my packet inside of my laptop, what do I think my source address is? 10.40. Yeah, exactly. Very good. What's my destination address that I think is in my packet that I can see as a user on my laptop? Excellent. Exactly right. 60.66. If I attach Wireshark here on this LAN cable, what do I actually see coming out of, and we'll call this A prime, what do I see coming out of my laptop? What's the source address? This should be an S, sorry. At point A, and this one's going to be at point A prime. So what do I see as my source address at point A prime? It has to be something the Sheraton will deal with. The Sheraton's not doing anything different. So here comes a packet across the Sheraton's Wi-Fi network to the Sheraton router. What IP address is the Sheraton router expecting to see this coming from? One that Cisco assigned or one that it assigned? Exactly. And what address is that? 10.11. And what destination address is the Sheridan router being asked to send this to? The VPN, 160.22. The last part of this, at point B, which is, outside, this is point B here. Outside the Sheridan router, the only thing that's going to be different here is the source is going to be 8.23, and the destination is 160.22. It has to be this way. This guy can't be asked to do anything different than what he ever has done in the past. He doesn't know anything about this. Okay? What does this user receive at point C? My packet is now making it to him. What packet shows up at his door? What's the source address it's coming from? Yeah, it won't be exactly the VPN. I do need to give you probably should give you one more piece of info. I think it would help here. I run the risk of kind of overwhelming you. This is running VPN. It's also running NAT because I'm using 10 dot addresses back in here, remember? And so NAT, let's say its public address pool is 160.20 instead of 22. So this packet is going to come inside the VPN. I'm going to get an IP address. It's going to get turned right around. It's going to be sent as if I was really here, out through the internet to Sportsnet. So the source address is going to be 160.20, and the destination is going to be 66.66. Yes? Well, VPN is the only thing we really use now, and it gave us all of these constructs. shim software, tunneling agents, all that stuff mobile IP came up with. We just packaged it up differently, and we call them VPNs now. But it's why this chapter is in the book, and it's why, even though none of you will use something probably ever called mobile IP, why we still teach this chapter. It would be better if they had a chapter on VPNs, but that's not part of TCP/IP. This one is part of TCP/IP. Okay? So if I want to tunnel someplace, now you guys know what's going on. The problem with showing you this on Wireshark is VPNs also do one other thing that we haven't talked about to this payload. What do they do to this payload? When it goes from here down to here, what happens to it? Anybody know? Let me give you a hint. What am I telling you is going on? It's encrypted. VPNs encrypt all of your traffic. So if I tried to look at a VPN packet with Wireshark, I would never see the second IP header. I would never see the TCP header. I would never see the application message because it's all encrypted. So there are no VPNs that will turn that stuff off anymore. All people want is more encryption, not less. But there are versions of tunnels that don't do any encryption at all. And one of them that's very popular is called General Routing Encapsulation, GRE. You can build a GRE tunnel, and in fact, that is usually, let's see, do they have it in here anywhere? They have it in one of these slides. They mention it by name. But I don't know where anymore. Okay, let's wrap up this kind of discovery. First of all, was that interesting and helpful, or one of the two at least? Did you guys ever know this? You kind of have the concept now? So if I ask you to kind of explain to me, you know, what's going on here, do you think you could? Okay, none of you said that 30 minutes ago. Right? Not a single one of you. So if we can hold on to that for a little while, then great. The concepts will link in. So The difference between encapsulation and forwarding or tunneling is encapsulation is the normal one layer to the next to the next. The numbers change. With tunneling, the numbers stay the same. This is still layer 3. Layer 3 to layer 3, and then down to layer 2, and then to layer 1. Okay, so a few things to wrap up on this. Obviously, this can be very inefficient. It already is, even just using WebEx. Anybody here use WebEx in class? You guys sometimes have it open, right? Okay, so we're behind the same router, 1 meter away from each other. In order for me to get a WebEx packet, like if I move my mouse or I draw on the screen or I say something, where does that packet go? It leaves and goes to Richardson, Texas, and turns around and comes all the way back. And it's encrypted in both directions with different encryption tunnels. It's VPN to there, and it's VPN back. You never know it because it's built into the software. It's the tunneling software is part of WebEx. But you can't, when we look at WebEx packets, you can't see the audio and the video. It just looks like data because it's encrypted. So that's very inefficient because we're sitting next to each other. But that happens all the time. You'll tunnel stuff. Sometimes you'll tunnel stuff to change what appears to be your location. There is no way to hide your location. You may try it with a VPN, but there are packets that VPNs will let through that will spill the beans. Things like, which time server gave you your time? It's going to be the one the router told you to use, which is always going to be one close by. So you say you're from San Jose, but it's very interesting, your clock was set by a time server in Monterrey, Mexico. I wonder if you're really in San Jose. So there's things like that. And as my buddy, the network engineer at Cisco, Ricardo, says, he goes, don't even try it. We can always find out where you are. I'm like, God, man, you're like creeping me out. Stop it. Yes. Mm-hmm. They never will. The VPN people are providing a service to you. They want you to use this for exactly that purpose because they know that if they can make sports show up, you will be on their site for hours and hours. You're never on other websites for hours and hours, except maybe a gaming site. So they want to put ads in front of you. They want you to click on some of the ads. Sometimes you do by accident. They get paid for that too. So what other thing could they possibly show you that would keep you there for hours, watching intently? And you can't ever step away because there's no pause button like there is for a movie. And so it's perfect. It's a perfect business model for these guys. So they're never going to kick you off. And they will never, the only thing that could happen is like Netflix could figure out that this site is a destination for a bunch of VPN tunnels for people who are trying to connect really from outside the United States. So what they can have is an employee who tries to do what I do, and my son does, which is find a place to watch the Houston Astros. So they can search around, they can try connecting, and they can just start making lists. This site is illegally broadcasting our performance, our game. This site is doing it. And they go back to their network team and they say, block all incoming IP streams from these IP addresses. And everybody's VPN just stops, or the game stops. You still see the ads and all that stuff's still there. So sometimes when you try to watch sports and you can never get it to work, it's because the people have already turned them off. They've already shut it off for them. It's very hard to do. So a lot of this stuff is not Googleable. It's shared via Twitter. I saw one the other day during the Astros game. This is the one that was like super excellent quality. In fact, I wonder if I can actually pull it up. I wonder if it'll work from here. So there was a guy whose avatar was a guy in a suit, and I think it was like his company or something. And somebody asked, like, how come you don't list the Yankees in your list of games? And he goes, oh, we have that, but it's private. Here's the link. And he put it in the little chat window for the guy. All right, so let's see. Here's Zach. Okay, where is he? Wow, this is like super, super slow. Is it gonna work? Okay, finally. All right, sorry. He's got his new bedroom. He's very excited. He's in a new city. He's got a new job. So you guys end up learning. He got a Bitcoin scam the other day. So he was panicked over that. It's a really nice apartment. I'm somewhere between proud and jealous. More proud. Okay. Oh, it was his birthday. So this billboard was out on Garavasada, so I sent it to him. Happy birthday to me. Yeah. Yes, May the 4th and 5th. If I can find someone to go with me, I will. In fact, I told him here, again, right here, just, June 15th, I come up, etc. Okay, where did he send me the link? I was complaining about the Astros. Here we go, yoursports.stream. Heard of it? So here's the game feed. Choose game. Let's try baseball. It's baseball, MLB live games. So it's like super duper slow. MLB live games. Let's see what it looks like. With all the garbage that people do. Okay, where's my Astros? Rangers, here we go. This is the one I want, and I want the away. Because I can't stand their announcers. All right, let's see what the quality looks like. So they
allows him to drive the ball off the wall. But again, when you're doing that, you're in sync, and you get the barrel to it, you hit baseballs that are 107.6 miles an hour off the bat. That was 107. Yeah.
And I can try doing it full screen. It almost looked like
you got a little too extended because it was a changeup. Ball got to the wall in a hurry. That's the third double of the series. He's had one in every
It's a little jittery, but I mean, my God, look at the path it's taking.
Correa looks right in 2019.
I'm also running WebEx on top of that.
Now, if you only can get the...
Okay. So I have to stop now because in another 5 seconds I'm going to cancel class if I keep watching it. Because, it's my Astros, man. Right? It's my Stros. Yeah, they're coming. Maybe if we're still having class that week, we can have class at the stadium and talk about how baseball is like networking and the bases are like routers, and when you go to have the mound visit, it's like a VPN or something like that. And we could have like popcorn be packets, and I don't know what beer would be, Wireshark or something. I don't know. I don't know what that would be. All right, so let me get us out of here. We have a little bit of time, maybe 10 minutes more, maybe 15, to kind of go through. We can, if you guys, let me look. I don't want to lie about this. No, this is going to take us more than 10 or 15, but it won't take us more than 20, 25. Do you guys want to take a little break, or do you want to keep going? A little break? Yes? Okay, let's do a little 10-minute break, and then we'll come back. So totally separate topic, so it's a total one. All right, so we need to go through a little bit of material in a chapter on unicast routing protocols, and you guys have seen a bunch of this stuff in Dijkstra's algorithm and Bellman-Ford before. So we'll go quickly and we'll sort of break things out. What I want to remind you is that there are different routing protocols you use inside of a network and between networks. And to make the internet a little smaller and easier to understand, what we do is break our organizations up into autonomous systems. You guys remember that phrase, AS numbers? You've seen those around? They were in last year's thing as well. So all of tech could be in one AS. It's not. It's in multiple, but not a lot. We have 50 public subnets, of networks, but we have, I think, 5 or 6 public AS networks. So instead of counting the number of routers that something goes through, if I want to show you what it takes to get to a site, I can do it like this. So let's say here's one network, and here's another network. And this network has a couple of routers at the edge and a bunch of routers inside. And so does this one. It has a couple of routers at the edge and some others inside. And I'm going to add a third guy in here because that's what the books usually do, is I'll put a third one in. And let's say there's a new network down here that we just discovered. And I don't know much about it, but what I have noticed is that I have a connection to it. And the connection is here. So if this is AS number 1, and this is AS number 2, 3, and 4, and people have AS numbers, you're assigned an AS number. If I want this person using this laptop to find help in reaching AS4, the first person to discover it might be AS1. And 1 and 2 have had connections with each other for a long time. Yes? Autonomous system. And it's basically an organization, a company, a university, a municipality, someone that runs a network that's in charge of it, where all the routers run the same protocol, they are all part of the same organization, it can all be treated as one connection to the internet. That's an autonomous system. And so it's a way of stepping back from some of the detail and just, you have a lot fewer ASs than you do anything else. You have millions of routers, but thousands of ASs. And billions of users, but thousands of ASs. So instead of trying to track all the network numbers, what we do inside the internet between these ASs is we just track AS numbers. I don't care about network number routers anymore. So what AS3 will advertise is, I know how to get to AS4. Send it to me. That's the route. And AS1 will receive it, and he will advertise to his friend, AS2, I know how to get to AS4 through AS3, send it to me. And so he hands him this route. So it's 3 hops, basically. So this user, armed with that, will take this path to get to AS4. If later in the day or some other time this connection is established, then a different route will be advertised here, which is, I know how to get to AS4, send it to me. And so now you might choose to take this shorter route. So here's the kind of thing that's sort of funny about this. We don't count routers anymore. So it looks like that this path is shorter than this path because I start at pink and I go through blue and I'm at green. This one, I start at pink, I have to go through yellow and blue, and then I get to green. But this doesn't mean that one of them really is faster than the other. It's just counting through how many organizations the packet needs to travel. So my packet might have to go through twice as many routers to get here this way. And if I take the other path, it might go exactly, like that. It might be straight. So it's not perfect, but we had to do something to simplify the network. And you can look up people's AS numbers. I can look up tech and see if we can find, it worked yesterday, it did not work earlier this afternoon, so I'm going to see if it works. AS, where's AS? What am I missing? There he is. Okay, this is it. So we can look up tech.mx. Didn't find that. Yeah, so it's not working. So it worked yesterday. Fortunately, I grabbed what I needed so I could show you. What I grabbed when I pulled it up was a list of, well, I pulled up exactly this list. It has our AS numbers, the name, the range. Oh, I know why it's not working. I think it is me. Check this out. Instituto will find one. It won't find us. Finds the one in Mexico City. They decided to give up accents for Lent. Come on, don't act like this. Here we go. So if I can add even more to that, Instituto Tecnológico. So here it is in Mexico City, right? If I just change this, good God, change it already. Whoops. Then it gets us. So here's the table that I found. I put it in a spreadsheet. We have several AS numbers: 6342, 10436, 7960, and 36. And the other thing this table shows you are the IP address ranges that you've been assigned. And it tells you the mask. So I wrote a function this afternoon that pulled this out and calculated the powers of 2 to see how many public IP addresses Tech has. We have 208,000 IP addresses, public IP addresses. We have millions of private. How many public addresses do we need? A couple of hundred. Why do we have 200,000 public IP addresses? Well, we may not get caught too soon because we also run the network registrar for Mexico, who assigns public IP addresses. So who's gonna stop us, right? Kind of funny that way. But it's a lot of crazy, isn't it? It's a lot of public IP addresses. So instead of publishing all of these networks, these 50-something networks, and putting routing tables in, putting these entries in routing tables, we will just publish AS numbers instead. And that's all we'll publish. I don't know why we have so many ASs, but those are probably parts of these other institutions. So here's a diagram that shows 3 ASs, and the routers that talk to the outside world, like these 3 here, they have to run 2 different routing protocols. They have to run one that talks inside the organization, and you can pick whatever you want to run there. And then they pick one that runs between organizations, and this one is almost always BGP. Well, it's the de facto standard BGP. So these routers have to run both types of protocols. So those are inter-domain, and they're BGP. Inside the domain, we run either link state or distance vector. This is closer to distance vector than it is to link state. But beyond this, you guys remember how some of this stuff works. With Bellman Ford, you take people's word on it. So if you have 3 different ways to get to J, you will ask each of them, what do you think it will take me to get to J? And you will add to their answer what it takes you to get to them. You'll only do this for routers that you directly connect to. So people can lie to you. They can send you the wrong kinds of routing tables or wrong kind of inserts. So there's a little bit of risk to this. It also doesn't do a good job of catching loops, but it's efficient, and it doesn't flood the network with millions of packets. The Dijkstra algorithms do. They require that every device on the network have a comprehensive knowledge of everything going on in the network. So they will flood the network with millions of packets depending on how many routers you have. Like if it's Xerox, they have thousands of routers, you'll have millions of packets probably. And they are all exchanging information. So each router gets a complete map of the entire network and builds its own routing table. So it's completely independent. It's not prone to being lied to or creating loops. It can spot all that because it's doing all the work itself. But it's a massive load on the network at first. It floods the network. So you hope if you're in a data center with a lot of routers, the power doesn't go off and back on because all the routers turn back on at the same time, and they're all just going to kill the network, right? So it's kind of funny. Okay, we have an interesting problem with some of these algorithms with Bellman-Ford, where you take other people's word on it. Whenever something changes in your table, you tell all of your neighbors, and they update their table. So it can lead to the following classic problem called the count to infinity problem. So here I have two routers, A and B, and a node X. And A advertises to all of his neighbors that he knows how to get to X. So he sends something out that says, I can reach X in a cost of 1. B says, oh, fantastic. I'll add that to my table. I can get to X through A, but I got to add my own cost here, so it's a cost of 2. But thanks for telling me. So this constitutes an update. B just updated his table. And the rule is you send the update to everyone. And this sounds stupid, but you send it back to A as well. Why? A is the one that told you. Why would you tell it back to A again? So here's the problem. It's possible B also discovered a path to X completely on his own that's better than yours. That's why B will tell A what he learned. So if B comes back and says, I got there in less than you did somehow, then A may update his table. So, but here's why that can get you into trouble. So now there are an outage. The link to X goes down. And so the cost goes to infinity. So both of these now have updates to their table, and they each need to tell the other. So there's a packet that needs to go from A to B and one that needs to go from B to A. Got it? Right? What happens if the one from B arrives first? I don't know why all these other links disappeared. All this other stuff disappeared. It shouldn't have. I hope I didn't do that. So let's say B's update arrives first. B will tell A, I know how to get to X in 2. Well, he can't anymore. But if he tells him that update first, then A will update his table saying, great, I know again how to get to X. I just send it to B. And he goes to 3. And he sends an update out. B gets the update and says, oh, okay, so I was using you before, so now I guess it's a cost of 4. So this goes 1 to infinity, but because this one arrives first, 3, 2, 3, 4, 4, 3, 4, 5, 5, and on and on and on. Count up to infinity. 1 by 1 by 1. In the meantime, people are wondering, like, what in the world is going on? Who's got a path to X? And nobody has a path to X. The link to X went down. So this is a problem with Bellman-Ford. It's a very famous problem called count to infinity. So you can do a few things about it. One of the things you can do about it is stop at 16. Just don't go past 16. You'll let this go on. Once it gets to 16, you'll just change it to infinity. It's like, that's enough. But what if it's really 16 to get there? Too bad. It's infinity. So that's one thing we do. We usually do it inside of an organization. So it's far less likely you're going to need 16 hops to get to the other end of your network. On the internet, yeah, but not inside your own organization. All right, so the other thing you can do is what's called split horizon, where you just don't send updates back to the person that gave them to you. Like, that seems obvious, right? Why would you not do that? And the last thing you can do is called poison reverse, which is kind of a cool name, where you lie to A. And A tells you he knows how to get to X in 1. You go, I know how to get to X in infinity. So you just purposefully lie about it. That keeps that from happening. They will never pick you. And so those are the actual names and the approaches that we use in routing to get this stuff done. So it's sort of crazy. They also have an example of a 3-node one that's a little too hard. So that's those are the algorithms, Bellman-Ford and Dijkstra. RIP is an old protocol. It's easy to learn, and you can sit down in a router and in 5 minutes start writing routes. You can read the code. You can kind of figure out what's going on. It's very simple. It is based on distance vector. Okay, so they walk us through what RIP looks like. We do not need that for this class. We do not need to understand how to program routers with routes. The lab may give you a chance to do some of that, but I mean, it doesn't make any sense to try to teach it on a blackboard. Like, here's what a route would look like. But they give you some examples of messages. The cool thing about RIP is if you've got a bunch of updates, you can just tack them all onto a really long message. You don't have to keep sending lots of messages. So it's a little better about that. They have different timers, different ways of getting updates. Periodically, you'll check to make sure you're still there and people still believe you. So those are like timeouts. We've seen that kind of stuff before as well. And you've got RIP version 2, which is the version that if anybody's still running RIP, that's what they're running. This is a pretty decent diagram of link state routing. You've got your ASs inside your network, but this is inside your own organization. So let me describe what this looks like. There are 5 routers in my company. This is how A believes they are connected. This is how B believes they are connected. The reason why they may at times look different, this is at the beginning, I guess. They would absolutely be different if this was finished drawing, but I don't see any differences between these yet. So what they will do is calculate their own table, and as you guys may remember from Dijkstra's algorithm, you end up with a different view of the network based on what the least path routing is. So I'll show you an example, but we'll do it like in 1/10 of the time it normally takes to do these, because I'm just going to jump to the answer. Dijkstra's algorithm. All right, so let me steal this, and let's just see if we can do it by staring at it. I may need help from you guys. So I want to build the routing table first for you, the letter U, not Y-O-U. Okay, so the routing table for you, which paths is he going to use to reach all the other routers? He's going to clearly use this one to get to W. What's his best path to V? I think it's the direct one, isn't it? What about to X? Also the direct one? 1632. Yeah, this is still less. Okay, what about the best way to get to Y? I think it's to let X go there. No, it's not. Yeah, it sure is. 1 plus 6. Right? And then what about the Z? It's got to be this. It can only be this one or this one, so it's got to be this. So here's the problem with this network, and this is the classic problem with destination-based forwarding. Yeah, I agree with you. Like that? So here's the problem. I have U that goes to V, W, and X. W goes to Y and Z. That's not terrible, but Z has a hop to go through, 2 hops to get to V and X. So he's sort of dependent, which is unfortunate because some of these may have other routes, like Y has to go through W to get to Z, even though they connect to each other directly. But the reason for that is because this is the routing table for you. Let's draw the routing table for someone else now. You want to draw the routing table for Z or maybe W? How about for W? Is that okay? How will W get to U? Same path, I think, right? How will W like to get to V? He's got 7 here. He's got 1 plus 6 here. So they're the same, right? But just to make this prove my point, because routing algorithms will arbitrarily pick this, I'm going to pick this one on purpose. Okay, what about W to X? What's the best way to get there? Yeah, I would pick 9 for now, but in a minute I'm going to discover that Y is a better path. So is my best path from W to Y this one? I hope so. And what about the Z? Same as before? All right, so my routing table for W looks like this. W gets to U and Y, and U gets to V, and W, let's see, Y gets to X, and W also gets to Z. Correct? Different map. So you paid for 10 network links. Neither one of these routers is ever going to use these 4. You might as well disconnect them if all of your traffic comes from W and U, because you'll ignore them. Why would you do that? It leads to some classic problems where if you're trying to get from here to here, and there's 3 choices in between, and each of these are 50 megabits in size, 50 megabits per second, and you have 100 megabits worth of data that you need to get here, what routing destination-based forwarding protocols will do is pick one, and that's it. You'll never get to send anything over the others. It'll never happen. So it's a huge problem. And the need to do that is called the need to do traffic shaping. And the phone company knows exactly what that is. They've done it for 100 years. You would never dream of building a system that didn't let you do traffic shaping. But we did. We did exactly that. So software-defined networking can change this because it will look at some of the source addresses and go, if it's coming from this part of the world, send it this way, otherwise send it this way, otherwise send it this way. Or they can do things like, look at the thousandths of a second on your clock. If it's an even number, send that packet up this way. If it's an odd number, send it this way. You can do things like that, which you can't do in normal routing today. So there's some interesting problems that we are trying to get solved with these routing tables. What you end up with at the end are different views of what you think the network ought to look like. This is their version of this type of graph of what's going on. Okay, I may have a little bit more, especially if I can find junk on VLANs, but I don't think any of it is here at all. So I think what we'll end up doing next time is start skipping to the stuff further into the book, like security or something like that. Okay. Question? Oh, okay. Oh, that's okay. You can stretch. Okay. You guys okay? Make sense? Okay. So we are up to chapter 11, which is not bad. We did okay. There's like 16 or 18 or 20 or 100. I can't remember how many there are. 30. 30 chapters. Wow. We won't, yeah, I know, like, really? Really? 30 chapters? So it makes sense, but we're not doing 30 chapters. It's too much. We'd have to do 2 every lecture. 2 chapters a lecture. That's too much. All right, guys, I'm out of stuff for us today, unless there's other stuff you want to talk about, other questions you have. How are the labs? Is anybody going? Are they happening? Are they okay? So you actually been touching things? Okay, finally. Okay, good. And are you routing at all? Are you programming routes? Sort of? Something that looks like that? Okay. Uh-huh. And you're setting up subnets and trying to ping each other. Okay, good. They go up and down administratively. The cost will change when that happens. Oh, you're doing both. Awesome. Next time? Yeah. So the ideas are similar. Addresses look really, really different. And you may have IPv6 addresses. You can go to websites and ask them, what am I using to connect? Like if you're behind a NAT router or something, and sometimes it'll tell you your site is using IPv6 to get to me. They do what they can. Mexico's taken off with IPv6 in the last 2 years. They had 0% penetration 2 years ago, and they had no IPv4 addresses left, not a single one, 0, for the Latin American Caribbean, none, for the whole area, not just Mexico. And now it goes up every month. So we can see what it is now. But it's pretty cool. Now there are 2,200,000 addresses back in action. So the reason why is because people are moving to IPv6 and they're giving them all back. They don't need them anymore. Or they're being taught how to use NAT because it's a lot more secure, and they don't need them anymore. And if I find the site at Akamai IPv6, here we go. Oh, there it is. Is this the one? Yeah, this is it. Let's give it a second and I'll show you what it looks like. Oh, do I have to click something? Yeah, that might help. Okay, no, here it is. Okay, it finally showed up. So Mexico was down at literally 0%. And you're at 25 now, I think. What in the world? 24.1. So you're number 22. It's right from number 100. So it's just amazing. Look who's at the top, India and St. Bartholomew. What do they have, like, did they turn both of their routers on and they still have one more left? Or how does that work? And then India, that's unbelievable. So, and then there's some countries down at the bottom that are highly developed and are way behind. So it's finally happening after 20 years that adoption is finally taking off. It was nothing for the first 20 years. And Mexico's on top of it, which is cool to see. It's kind of surprising once in a while. We do okay. We do okay on stuff. Hold your head high. All right, guys, thank you very much. And I will stop the WebEx.